Dr. R. Ravi Varman. The proper introduction of Dr. Ravi Varman will be given by Mr. Who, sir?
Yes, sir.
Aravind sir will give the introduction of Ravi Varman sir.
Yes, sir.
Please take
over. Good afternoon, one and all. Myself, B.R. Aravind Raj, Assistant Professor from the Department of Mechanical Engineering. On behalf of Department of Mechanical Engineering, Veltech Multitech, Dr. Rangarajan, Dr. Sagundala Engineering College, Avadi, Chennai. It is my great pleasure to introduce Dr. R. Ravi Varman, Assistant Professor in the Department of Mechanical Engineering at NIT Agratala. He has completed his PhD degree program from the Department of Mechanical Engineering from Pondicherry University, and he is the gold medalist person for his MTech program from the product design and manufacturing stream. Dr. Ravi Varman sir has a research experience of more than 8 years as well as in teaching also, and he has made a significant contributions in the computational mechanics, finite element analysis, gear design, tribology, and mechanical system simulation. He has published notable and significant research articles in reputed international journals, presented significant papers in national and international conference, and he has authored for 4 books chapters published by Springer and CRC Press. He is also an DST Inspire Fellowship awardee in the year of 2019, and he is an active reviewer for leading journals like Elsevier, Springer, and Sage, and the recipient of funded research projects from national agencies. We are honored to have him with us and to share his expertise and insights in the topic of green composites, types, degradation, and characterization. I welcome you, sir, for the session.
Thank you, Arandra, sir. The session is yours, sir. Ravi Varman, sir. I will stop sharing.
Good afternoon, all. Am I audible?
Clear, sir. Clear, sir.
Yeah.
Yes, sir.
Thank you for the warm welcome. So, as the introduction, myself, Dr. Ravi Varman from NIT Agartala. So, working in Agartala for more than 3 years. So, today my topic of presentation. So, before that, I will share my screen share. So my slide is visible, na? And the slide movement is
clear, sir. Clear.
Okay.
Everything is okay, sir.
Fine. So it will be a 1 hour session and extended discussion. So we are meeting at exactly the lunch time. So I hope people will not get distracted. So I'll try to keep engaged. So today's topic is green composites, its types, degradation, and characterizations. So what we work in NIT Agartala under this green composites, and what our future directions of research towards this, so which will be given in the end of the presentation, right? So coming to the introduction, so as you are all attending this FDP program, and you might be aware, as the faculties, we might be aware what is a composite. So I'm just touching a little bit. So the composite is defined as a multi-phase material, and the composition of material differing in compositions, which remain bonded together. So we have matrix, and then we have the reinforcement, that is the fibers. So these composites are engineered to meet specific applications, performance, and specific needs. So we know that this composite has been largely used in the automobile sector, aerospace sectors, where the material is getting replaced by the existing materials for its better performance, lightweight, and its good characteristics. So mainly you see that these aerospaces, we want to reduce the weight of the uh, whole machines, so or the components in the aeroplane. So we are going for composite material. So we study this composite material in different ways, combining different materials which are synthetic one. Now we are moving towards the nature based material, that is the green composites. So green composites, it's nothing but the combination of plant fibers with the natural resins to create a natural composite materials, so replacing the synthetic ones. So here you can see the biomaterial composites which are made from canaf, sisal, soybean. So these are the natural fibers which are emerging as a low cost, lightweight, and apparently environmental friendly. So which is the major thing in the recent days. Like the government policy is also focused towards it. So environmental and sustainability concerns, which are the pivotal drivers in the development and adoption of these green composites. So government is not even government. Overall, the world is looking for some alternatives so that we reduce the greenhouse gas. So here we see that these natural fiber reinforced biopolymers are known as green composites, are made majorly from bioresources. So they will be having a matrix, which is a bio-based polymer matrix, and a natural fiber in combination, which be generally producing the green composites, which are more advantages, like they are less expensive and having a reduced weight, better performance, and then they can be tailored to the requirement. So what is our functionality requirement? Based on that, you can able to manufacture it, and they are from renewable sources, which is good for the environment. So here you see that these resins and fiber, once used, they are biodegradable. So generally they come from this natural sources. So obviously they are biodegradable. So when they are dumped or decomposed by the action of microorganism present in the soil, so then it can be converted into H2O and CO2 and absorbed by the plant system again. So it is a recycling one. So these two main components are very much important for this. So here you can see the various types of natural fibers. So three based natural fibers. One is cellulose based, animal based, and the mineral based. So cellulose based is we have variety under it, like a bast, fruit, grass, leaf, seed, stalk, and the wood fiber. So we have been using many like jute fibers, coir. So we have a separate coir mm, policies given by the government, yeah, and they are also funding largely for the researchers based on coir fibers. So they are using as the sustainable material. So similarly, here we work with bamboo fibers. So in the location of the Agartala, that is in the northeast regions, so we have abundant sources of bamboo. So we work with the bamboo fibers. Then we have the sisal, banana fibers. Banana fibers, most of them are aware about it. So how they have been used, banana fibers from our very old time. So we are using the fibers separately. Now we have this disposable plates, and then using the fibers in the form of long fibers, short fibers, or mat forms, which we are using it with the biodegradable polymer matrix, so that they can able to produce the required components. So similarly, we have like cotton, then softwood, hardwoods, and animal based like wool, silk, and animal hair, mineral based. So all these pictorial representations are also shown here. So in different formats they are available. So we have been using it for our day replacement in our day-to-day life using these natural fibers. So here you see the life cycle of a green composite. So why we call it as a green composites, or the life cycle, that is it should have a circular economy, right? From the initial stage of development to its decomposition, like we get the natural fiber extraction, and the just I will So here you see that the fiber extraction, and then the different forms of natural fibers and the polymers, and the composite developments. So we generally call it as NFRCs, natural fiber reinforced composites. So they are fully or partially biodegradable, used in majority of the application. Rather, after which it should be disposed and composed, so that it has a good biodegradable properties, so that he can able to go as an input or the energy source, again completing the cycle. So here you see they are generally made of or these are the resources from natural one. So they are low energy consumption one, so eco-friendly composite manufacturing. So when you see the LCA component of it, so life cycle analysis, when you do, you can see that these green composites are better in that. So widely used in automotive and construction and packaging industries. So and it drastically reduces the carbon footprint compared to the synthetic composite, right? So there, so you know, or you are aware that the composites are made up of two phases. One is the matrix and the other one is the reinforcement. So what about the polymer matrix phase? So here you see that there are different or majorly they are categorized into two types. One is the non-biodegradable and the biodegradable. So in biodegradable, uh, so what we are looking into it, whereas a non-biodegradable is the one which is existing, that is the synthetic one. So in so we so there are different types under it: thermosets and thermoplastics. So thermosets which softened and decompose on heating, so which does not convert and it cannot be reshaped. So you know, epoxy and other things. Similarly, we have thermoplastics, so which can be melted and heated and then cooled and been used. So majority of the places we see this, right? But our concentration is towards the biopolymer. So majorly it has been characterized into two types. So one is the biothermosets and the other one is the bioplastics. So you see here why these biopolymers are getting its importance is majorly their degradable characteristics and the resources in place of the synthetic polymers. Moving towards the ecological and sustainable perspectives, these biopolymers are derived from renewable sources or living organisms majorly, and their biodegradability is influenced by polymer and the polymer physical and the chemical microstructures. So biopolymers here you see they are categorized into thermosets and thermoplastics, as I said. Uh, so these biothermosets polymers which undergo irreversible cross-linking during curing, resulting in a high stable three-dimensional network. So here we have bioepoxy resin, biopolyurethanes, phenolic resins, unsaturated polyesters. So which are good sources like one you see here bioepoxy resins which are synthesized from bio-based feedstock such as lignin, cardinal vegetable oils. These resins which are widely used in coatings and adhesives and are also used as a matrix materials in structural composites. Uh, through the reaction between polygols and the isocyanates, so which is also on bio-based natural sources like castor oil, palm oil, soybean oil. Okay, so similarly, biophenolic resins, so which represents the thermoset category one. So here you see these are replaceable one instead of the petroleum-based phenol formaldehyde, which has been used in the synthetic one. So we have extracted from wood and bark and used as a renewable substitutes for using it in the bio-based places. Then the polyesters, so which have been uh, extracted, okay, from plant oils, so which offer improved sustainability compared to petroleum-based or unsaturated polyester resins. So again, we have this the other type like biothermoplastics. So similar to the non-biodegradable one. So here the family constraints of PHAs, that is polyhydroxide alkanates, which are naturally synthesized by various microorganisms, intercellular carbon and energy storage, and we have PHB groups also under which. So one of the extensive used component is a PLA, which is can be manufactured easily. So the resources is from starch, and they have good toughness, thermal stability, and degradation rate. And our research was also focused towards using biopolymer polylactic acid PLA in our composite as the base matrix material. So here you see the application of natural fiber based composites. So we are using variety of the places like the car bumpers, floor protection trims, aerospaces, so thermoplastic components. Like you can see that by which research wise we see we are also trying to replace sense like machining property, drilling capacity, so that it can be get fixed to this things. So similarly in cars, lightweight car doors, natural fiber panels, and in roofing applications also. So we can able to see the applications of this natural fiber or green fiber based composites. So as the we come to the processing technique, so biopolymer plus you see natural fibers in different forms, long fibers, short fibers, and the powder fibers. So we have different methods in producing it, like the hand layup, casting technique, extrusion process, and then process like 3D printing, compression, filament winding, resin transfer molding. So all the process we can able to produce it. And the green composite, so as we are discussing, it is renewable and sustainable and high specific strength and degradable. That is the important characteristics, and used in majority of the applications like packaging, structure, construction, automotive parts, sports, uh, textiles, and furnitures. So here you see that was speaking about the bamboo composites. So these bamboo made materials like bamboo towels are nowadays you can see advertisements also. They are making these bamboo towels. So we because of the characteristics of the bamboo, say they are good observance of water. So bamboo processed materials as cloths are also available nowadays, right? So here you see this pictorial representation of the processing technique. So here you can see that from the from the circle diagram, here you see that the injection molding, extrusion, compression molding, filament binding, pultrusion, and vacuum assisted RTM, resin transfer molding. So all these methods, so we can able to produce it. So I think you are aware of it. Like you can see the compression molding method, which is the majorly used technique, where the material is shaped under pressure in a mold, then binding, where filaments are wound around the mandrel to create a composite structure, pultrusions, similarly injection molding, where molten metal is transferred into a mold and to form a shape. So the process is shown here, where the mold and the material which is being flowed to the inject so that it occupies the mold. Similarly, we have the compression molding and the filament winding process are shown here. So where the fibers are supplied as a continuous strands into the base resins, after which it has been converted into the required. So here, as various processing technique we are using for the conventional one or the synthetic one. Here also we use the same one for the green composite, but we the materials used are the environmental friendly materials or the materials which is available from the natural sources. So characterization technique. So here we use to want to analyze the mechanical and the physical characterizations. So characteristic properties. So what are the characterization process we should. So we are using FTIR, so Fourier transform by infrared spectroscopy analysis, transmission electron microscope TEM, then atomic force microscope AFM, XRD, X-ray diffraction analysis. TGA, SEM, density measurements, and we also added bed surface. So here you see that the FTAR used to explain, give detailing about the chemical bonding and the functional groups of the present in the sample. Similarly, TGA or DTG, thermal stability and the decomposition temperatures of the sample, what is the heat absorption and the exothermic behavior, surface morphology and its structures. So whether there is fiber pull-outs or any voids present, so we can able to see using the SEM and the TEM. The crystallinity index and the fiber structure. Similarly, the density measurement, which has been used to know the density values of the individually and also the for the composite. So here the main thing or the main focus is biodegradation of polymer. So you see that the polymer, that is the synthetic polymers, the characteristics of degradation is very less. So um, here the biodegradation of polymer, that is the biodegradable polymers, we actually say it like that because they have good degradation characteristics. So in our work also we have studied the biodegradation. So so we are aware that the biodegradation, the plastic when placed with the microorganisms, so they break down. So the chains break down and they form surface erosion happens so that the enzymes present will be out and the water soluble intermediates or the degradation will be happening in the surface level. So which will be these enzymes will be attaching to the surfaces and they cleave the polymer chains and exertion of extra cellular enzymes. So they will be breaking down into metallic products like CO2, H2O, and methane. So, so these degradations, so we'll be discussing with relative to our work. So deeply what we have done and what we have identified in it. So So initially, we have utilized this PLA and the canaf and the bamboo fiber mat. So we used um, natural fiber mats in our it, and the technique we used is the compression molding for processing it, and the raw material was matrix. Okay, so PLA raw material, that is the PLA material in the form of granules we got it, and then we used using the compression molding material we converted into the sheet. So in the conversion, we have used the canaf and the bamboo fiber mat. So and then we hybridized, and again we used the compression molding machine, and then we developed the hybrid green composite in the form of stacking like KBBK. So why this specific stacking order? Because we studied, so you can refer to the paper which got published in biomass and biorefinery, biomass conversion and biorefinery. So where we studied the stacking sequences like KBBK, BKKB, or fully bamboo, fully enough. So why we are varying the stacking sequences by dual materials we used. So major our concentration was with respect to bamboo, but bamboo has some disadvantages. So to like they are good moisture observance, as I was telling, like bamboo fibers has been used in the towels as they are good observant of moistures. So here we use this bamboo in the mid layers and canaf in the outer layers so that the water absorption is getting reduced. So it has better diffusion uh, value. Sorry. So here you see that. So when we use this raw fiber hybrid composites, so in the mid process you can see this was the initial process we tried, and in our work we varied the stacking sequence and we found the optimum stacking sequence by keeping the mechanical properties as the output parameters. So we measured the tensile, flexural, impact, and the hardnesses. So after which we come to the conclusion that the stacking of KBBK was best combination in compared to the other stacking sequence. So after which we studied the other properties like post properties and its degradation characteristic. Now you can see that the material is not getting the expected strength or providing the expected performance. So we were trying to enrich or increase the properties by adding some pre-treatment to the fibers. So and similarly adding some nano composite HNT components. So alloy site nanotubes, so which has been added. So these are this also bio-based one. So which was added in the form of powder. We received it, then we converted into pellets and fillers. So after that, we went into. So it got pushed into the twin screw and extruded hopper. Post which in the polymer strands, then pelletizer. Finally, it converted into nano-filled PLA granules, so varied the percentage. So we kept it at a low loads, like from 1 to 5%, and we checked what it is influencing. Yeah, obviously we had a better performance, like the all the properties got increased, like the surface characteristics. So as the fiber mats were surface treated, so they are having better physical properties, and it was performing well. But the way like synthetic one, the biodegradation characteristics was got reduced because of this addition of nanofillers and the fiber treatments. So here you can see. So initial fabrication, so like canna fiber, bamboo fiber mat, and the pre-NA values combined in. So their individual tensile strength and percentage of elongation and its break percentage, density, and Young's models are shown here. So which were being used. So we have used it in the mat format. So the morphological characterization of the fibers was done initially. That is the SEM micrograph images showing the outer layer of the fibers. So here you see that able to see the presence of non-cellulosic substances, so which were removed after the treatment. So it was better performing in terms of physical characteristics, so which was being studied by the SEM micrograph image. So post which the FTR and morphological characterizations examine the dispersion of HNT filler in the PLA matrix, like same images showing the neat PLA or PLA with different weight percentages of HNT having HNT distributed in it. And similarly, FTIR spectra was also showing this peak, see the observations for the HNT, which is being seen here. The 10320 peak, which is very specific for the HNT, were also seen here, confirming the addition of HNCs into the PLA. Similarly, the other peaks which is present in the PLA were also seen in this thing, confirming the presence of HNT component in the PLA. Similarly, the particle sizes were also evaluated, and the standard is shown here. So here you can see the important thing that we were focusing about the degradation characteristics. So the degradability, how these composites are degrading and not giving their performance. Without giving their performance, how they are good in having a better degradation property. So that was the main focus of our study. So here you can see that the mechanism of degradation in KBB composite, that is Kenaf bamboo polylactic acid composite, is shown here. So original samples when placed in soil, so for 90 days. So here you see that during the soil burial duration, sample undergo biodegradation due to the presence of moisture. So here moisture and microorganisms in the soil, so which result in an enzymatic activity that leads to the reduction in weight of the samples. So the mechanism which works under this polymer degradation involves breakdown of the molecules into lower molecular weight products, which helps to convert into in some monomers. So the resulting lower weight molecules might enter the microbial cells, so which assimilated this into a biomass and eventually mineralized to produce energy. So the main reason for degradation of the untreated KBB composite, here you can see that. So like we have used H0, H1.5, and H3, where H0 is explaining that they are like without any nanofillers, 1.5% of nanofillers added in PLA and 3%. So here you see that obviously the weight loss for 30, 60, and 90 days or so. So here you see that almost the weight loss was like 18% for the 90 days for the one which is not having. The weight loss got reduced. Okay, the final finding that chemically treated and HNT added, having one, the weight loss is being reduced. But it is not like same as that of the synthetic polymer, though it is reduced, it is also degrading, but the degrading time with respect to synthetic polymers is better. So what happens, the degradation of untreated in the soil burial test, as they have good hydrophilic behavior, like canaf and bamboo have good hydrophilic behavior and weak interfacial bonding, so they get degraded very quickly. So this weaker bonding creates channels in that, so that they absorb the moisture and transfer through capillary action from the soil to the composite, allowing the growth of microorganisms, so that the degradation happens. Okay. So whereas the uh, the other one, like treated one, or which I have shown here, like when we use this processes, like adding treatment to the fibers, similarly adding HNT nanostrand. So what happens is their degradation is getting reduced. So we can also see this comparisons in the same micrographs. So after 90 days, we have taken the biocomposite structure by decomposing it, though the agglomerations, fiber exposure, and matrix. So which proves that the matrix is breaking and the component is degrading. Okay, so which has been confirmed by FTA spectra also. So this degradation character, like so this values before and after degradations has been shown here. So we have also used the optical microscopic studies, and then SEM micrographs, FTIR, similarly the physical properties, all the comparisons has been made. So like water absorption characteristics. So here you see that water absorption characteristics, so we have to increase it. So like the or it should resist more. Like the treated composite is obviously having less, that is more weight gain, so that which is having a less resistance to water, whereas the filler composite having more resistance to water, that is mainly because of the HND structure. So where this forms a tortuous path, so that the water or the gas molecule form has to move into it. So this is resisting that. This structure of the HNT is be acting as a barrier for the fabricated and the water absorption percentage. So here you see that the diffusion coefficient is getting reduced and the weight percentage is also shown here. Similarly, it has better thermal characteristics also, like the final peak degradation is getting increased, and onset temperature is also delayed, say from 200 degrees Celsius for an untreated one to 245 for a treated one with NaOH treatment, or better one for HNT filled one. Like you can see it in the TGA results also, which shows that the composites, green composites, have better properties, and also its degradation behavior. Like the degradation characteristics is also lost. So it is getting better physical thermal characteristics, and from the in the sustainable Canaf bamboo polylactic acid hybrid biocomposites, and but its degradability is also not completely lost. So we have also worked on the post degradability and surface characteristic study. So one we done with the water contact angle test. So here the contact angle was measured on the surface. So showing that uh, the H0 sample having a higher value and H2 sample having a lower value. So having better surface roughnesses. So the surface roughness you can see here. So it is almost 1.31 and raising to 1.66 for HNT1. So and bed analysis, sorry, surface area is also shown here. So 1.2 to reducing it to 0.61. So the pore volume and the pore density characteristics. So the pore diameter in nanometers is shown here. So all this supports the biodegradability, that the degradation is happening, and the degradation is good compared to the synthetic one, and it is not lost completely. Okay, so which helps us to retain the sustainable characteristics of the these green composites in par equivalent with the non-conventional one, which is or made with synthetic one. So they are better and also having good degradation characteristics. So the mechanical characteristic comparisons also you can see here. The mechanical characteristics of the composite with different percentages of HNTs are shown here. So here you see the neat PLA. So what is the tensile strength and the percentage elongation. So when you are adding more or the doing treatment to the filler, and then doing treatment to the fibers mat and then adding HNTs. So but the suggested that 3% HNCs are creating agglomeration, so that their properties are getting reduced. So it is advisable to reduce it or to maintain it in the low percentages. So similar to that, we have the flexural strength and the flexural modulus. So it was suggesting that 1.5% of HNT added in the PLA hybrid composite with canaf and bamboo as a better um, mechanical properties. So the confound by the same microstructure and the particle distribution for tensile, flexural, and fractured specimens. So here you see that good interfacial adhesion, fiberful loads. Okay, so with uniform distribution, whereas when the percentages are more, like HNT percentages are more, the agglomeration is more. So which with some fiberful loads, fractures, and then fragmented surfaces are also seen in this. So which has been reduced when you are using optimal percentages of HNT in it. Yeah. So so it's obvious that so HNT and good surface treatment to the fibers, it's going to enhance its performance, and also having a degradation characteristic, but not losing it completely compared to the sustainable one. So these are the influences. So as I told, the wettability conducted using the contact angle method, which showed a decrease in the contact angle with an increase in the roughness value in this sustainable composite, which demonstrated good biodegradability under soil conditions. So the highest weight loss without HNT. So indicating nanofiller addition reduces degradation, but reduces in a percentage value rather than not losing it completely. So confirmed by the FTAR spectra before and after soil burial with decreased intensity of carbonyl and hydroxyl bands signifying polymer matrix breakdown. So post-degradation analysis reveal matrix breakage and fiber surface exposures, organic carbon content obtained from elemental analysis, and a reduction in hardness, and collectively confirming the biodegradation under natural soil conditions. So similarly, the mechanical strength got enhanced by 40% and 50% in terms of tensile and flexural strength for the alkali treated HNT added composite. Yeah. So which is better, and this results represent the feasibility of this material, so enormous potential in various applications, majorly in sustainable construction field and eco-friendly product development. So we are also working in developing some sustainable roofing materials. So On the other part, we have also studied the tribological performance analysis of this KBB composite. So the study which investigated the development on a tribo material by replacing this HNT by reinforcing the HNT into the PLA matrix. So the combination is being shown here. So the experimental plan and the tribometer, which have been used by the study, where the direction of the normal load and the sliding surfaces and the specimen holding portions are shown. So, so we used the Takuji L27 array. So all the combinations we have selected, and we studied about the um, effect of load and speed on the specific wear rate and the coefficient of friction. So how it is going to perform. So the analysis of specific wear rate showed, so you can see in the plot that for the increased speed and the increased load, the wear was less. So which was supported by the some micrographs. So and how they are getting enhanced, similar to the other ways also, like the average coefficient of friction for the varying load and speed is also shown. So which forming this films between the surface and the dip. So here you see that the exposed fibers, wear tags, and the wear particles, the complete wear mechanism. So we have discussed about it. So the crack formations or the micro lines or the parallel grooves on the wear surface and delaminations were visible. So shown in the ones and surfaces. So showing the explaining that the wear resistance has been increased for the higher speed and the higher load for a H3 sample. So for the sample having optimal percentages of HNT into the polymer matrix. So to confirm that, we use this Pareto optimization. So Pareto optimization, it is a multi-objective optimization which was executed using non-dominated sorting with Pareto front. So employing MATLAB, we used it for the implementation purpose. So here you see that we can also use GRA or particle swarm optimization and overall evaluation technique, which was also we used in one of our study. So what was the main objective in implementing this one? That is the Pareto front is to the relevance in both. That is the straightforward and the complex optimization contents. So the optimal Pareto front determines the most advantageous collections of input parameters. So which lies in this front by analyzing the output parameters. Okay, so irrespective of the weights attributed to the specific output response, the optimal solution will invariably reside among this one, like the SWR and the COIF. So its weight percentages were has been added. So in the multi-objective optimization for executing these non-dominated sorting. So for identifying the optimal solution in multi-objective optimal way by by categorizing the population into various domains, so which helps us in attaining the solution with equivalent rankings. So here we have used equally optimum. So whereas we can also vary it and use it. So consequently, so we made a comparisons in continuous solution referred to Pareto friend A and B. So the two solutions and the distinct Pareto friends P and Q, which you can see it here. So it's been used that one is the speed and the other one is the load. So the flow chart that you can see, the flow chart here, which is illustrating the procedure to derive the Pareto front and what is the procedure we have used in our process. So here you see that least SWR and the COF. The least SWR and the COF has been found um, for all output responses, which yielded 5 non-dominated options. So for the first Pareto front, and then the second Pareto front, and the third Pareto front, this has been shown. So this pi sets of input parameter will yielded the optimal results for any assigned values. So the fitness function we have evaluated, and then come to a conclusion that this 1.5 percentage HN sample at a speed of 3 meters per second and at a load of 30 Newton has a better specific wear rate and coefficient of friction, COF also. So in terms of fitness functions. So any disturb, any questions?
Audience, now the session is open for the question to discuss
No,
with the expert member.
I'll complete it. Actually, some distraction I had. Still few
Okay.
more slides are there.
Okay, sir. Thank you so much.
Uh, so some disturbance. Somebody was calling it.
Yes, sir. I muted him, sir. No issues. Now you can continue, sir. Thank you.
Okay. So the inferences, the tribological, so here, as I said, the tribological properties enhanced considerably through the integration of HNT filler when compared with the unfiltrated composites. So here the optimum HNT was found to be 1.5% for the minimum specific wear rate and coefficient of friction. So at a higher load, so as we said, like 30 Newton and 3 meter per second using the Pareto optimization has been evaluated and confirmed by the same micrographs. So we like this all the works what I have discussed so far, like made through some sustainable natural fibers and the biopolymer matrix. Now we are in the working in developing as a product. So here you see that we are working to develop as a spur gear or the gear components. So replacing the metal gears with some customized material like for specific tailored application, but majorly from the sustainable one, like filament tear, like we are coir based or the uh, it's like sustainable composites, like that the major problem of these polymer gears, like they lose their properties at when they getting heated up. So that gears are always contacting elements. So what happens, they used to develop temperatures between them. So that we use a lubricant and everything. Still they further loosen its strength. So here we are working in developing this or using this sustainable materials in place of the polymer gears uh, by adding better strength to it, rather than also getting it by how we are incorporating is we are bringing in this concept of non-standard gear tooth profiles so that it has a better strength. So we know that the standard gear tooth profiles will be having a zero point 0.5 module in the tooth thickness along the pitch circle. So we are varying it. Similarly, we are also using different pressure angles on different sides, like core side and drive side. So that we are developing this non-standard asymmetric gear tools, so and non-circular gears, so which in the polymer gear, in the replacement for the polymer gears. So we are also so the application of non-standard and asymmetric gears, so they are being used by developed by Alexander Kapilovich, which has been used in the Russian aeroplanes. So here you see that the teeth and all, so they are not axis symmetric, and similarly, the polymer made test gears, asymmetric gears, are also shown here. So currently, these gears are made from SLS, so polymer material, in 3D printing. So we have studied. So we are in the process of studying this printing directions, that crack development of these polymer gears. So now our focus will be to incorporating the design concepts, like whatever I have shown, that asymmetric and the non-standard gears, correction modules to the gears, so that we use the sustainable products using the sustainable materials like natural fibers and the biopolymers, we are going to enhance the thing, like by studying the layer orientations. So majorly it will be not from the conventional process, because you know that the tooth rack cutters has to be developed like conventional process, but here now the additive manufacturing it's getting is important. So this additive manufacturing based process composites using sustainable materials or the green composites, we are working towards developing this gears. Okay, so that is our next focus. So all the samples what we made we will be utilizing. So whatever I have shown it for this green composites. So we have tested in terms of samples. Now we are trying to test in terms of as a product. So how this product is going to work and the performances in terms of product that we are working under it. So you can see that our team of my scholars and myself currently working in the research areas. What I have majorly shown here, like I just touched the introduction. So I just touched the introduction of green composites, types of fibers, and immediately I went into our work, what we have been doing it at NIT Agartala, and what our research focus is moving towards. Okay, so these are some of the references, so which I used for my study, and so thank you for this opportunity. So I'm open for the interaction with the participants. So any questions?
Sir, myself, Dr. Muthukumar here, sir.
Yes, sir.
How are you, sir?
Yeah, good, sir. Good, sir. How are you, sir?
Sir, regarding green, fine, sir, fine. Sir, regarding green composites, do we need to take any extra measures so that it is able to be continuously sustained for a long time in terms of material inflow, sir?
In terms of material inflow, you're asking?
Yes, yes, sir.
So initially, so I have also shown you that flow diagram or process flow diagram. So like here in our work, you can see that initially we procured this raw fibers only without any treatments, that directly for processed one. But as you said that these one are natural based one, so they are not having the expected properties. So we are in the position to enhance it so that it sustain that things, like as you said. So we used some chemical treatment for the fibers in the preliminary stage, so that so we have different options in chemical treatment. So in our work we have used the NaOH with 5% concentrations, so that we can able to increase the or reduce the characteristics of the sustainable things, so that it can have a better performance.
Okay, sir. Nicely answered, sir. Dr. Ganapati, sir, or Aravind Raj, sir, any questions from the audience? Sir, I think the explanations of green composites and processing, everything was good. Any questions from the audience? Okay, sir. Meanwhile, they type the questions. It's my duty to thank you, sir, for having agreed to deliver this particular expert talk.
Sure. Thank you very much.
Sir, I should be thankful to your friend Praveen, who has given your contact, and I met him in the FDP session in Manakula Vinayagar College.
Okay,
So
sir.
I
No
hope
issues.
our
You
our
can.
connection will be long lasting. And even when you come over, I think you are on way to your native. When you
Yes, yes.
come to our place like Chennai, do make a visit to our campus. Our campus is in Avadi. We have
Sure,
three
sure, sure.
institutions, a Well-Tech
So
group of
you just call
institutions.
me in any occasion. Ah,
Yes, sir. Yes, sir. We'll be happy to host you for a session here.
sure, sure, sir.
Particularly, this your field of research is
I
very
think.
vibrant, sir. I also, yes, sir. Yes, sir.
I think your any other opportunities, you just call me. So we people now currently we are also working on composite simulations. So
Okay.
in ANSYS, that part also we can able to.
Sure, sure, sir. That way we can also touch upon the design and simulation.
Sure, sure.
Thank you very much, sir. Thank you for your wonderful session. So, participants, this is the time to say goodbye to our expert here. So, other participants, please stay here, sir. The speaker will be leaving.
Okay, sir. Thank you very
Thank you,
much.
thank you.
So
Yes, sir.
thank you for the opportunity once again. I thank the coordinator. And any questions? I think there are few questions. So in the comment section.
Sir, there is a question before you leave, sir. There is a
Ah,
question in the chat box, sir.
yeah. Just I saw
Uh,
the pop-up
I'll
message.
read. I'll read for you, sir. How do green composites compare with the glass fiber composites in terms of strength and stiffness? What is the effect of fibers length and volume fraction on mechanical performance in terms of thermal? What is the thermal stability limitation for green composites? Is asking comparison with the existing fiber and the green composite fiber, I think.
See, actually speaking, these glass fiber composites are better performing composites compared to the green composites in terms of strength and the stiffness. But the major focus is towards this sustainable characteristics and other things. So green composites will be difficult to match the performance of a glass fiber composite or like volume weight basis also low density they have. But there are also some better performance composite some hemp, jute. Okay, so these are like we have to reduce the um, errors, or you have to be careful in reducing the voids, having a better interfacial bonding between the fiber and matrix, so that we can achieve or in par achieve equivalent to the strength and stiffnesses. Currently, majorly we are using glass fibers, but government is focusing towards using these green composites. So these green composites will also train. So we are using different techniques. Like in our work also, you can see that we use this hybrid composites. So in hybrid composites, we are using different layers. Like one layer can have one layer bamboo, so one layer jute. So in terms so that we can able to combine this or tailor its performance and achieve in that terms. Similarly, in the effect of fiber length and that is actually, I think it is a general question, or it is in terms of green composites. I don't know. So how that fiber length and volume fraction, which is going to uh, play a role in the mechanical performance. See here, you see that when you increase the fiber length, so generally. So the load transfer will be better, so there, there will be a good load transfer. So when the fiber lenses are more, um, but increasing the volumes may increases voids and other things. So it is better not to go beyond the higher volumes of fibers. So so we also studied like 30%, so like 25-30%. So there are studies, there are many paper published with respect to this volume fraction, so which will be lower. So studying with the literatures, so optimal percentage can be taken, so that we can able to reduce the voids and other things. So in terms of thermal characteristics. So the thermal stability limitations of a green composite. See, in green composites, generally you see that in TGA, we used to get this peak degradation temperature. So this composites are having less heat resistance compared to the synthetic one. Say, when you take like a sustainable thing we want to produce, so the decomposition temperature is less. They are hydrophilic in natures, and they are poor interfacial bondings, and they are, so all these concerns are there. So that's the way we have to improve it. Like we are using like nanomaterials or the preliminary treatment processes, so to improve its performance of the green composite. Directly, if you use like the work I presented here, it has 3, so I can also show you. So here you can see that. So the thermal stability. So here you can see the untreated composites and treated composites and the filler treated composites, how it behaves with respect to the thermal characteristic. So the filler treated has better peak degradation temperature, and the final temperature is also increased at the onset temperature, whereas the untreated one at around 200 degrees Celsius, the onset starts. Okay, it's the weight start to reduce, whereas by adding HNT or doing some treatment, we can able to enhance it, so that the property, the material may be a green material, but we use additional things like additional um, treatments or nanomaterials, so that we can able to get the performance in par equivalent to the synthetic ones, not losing the biodegradation characteristics. So these are the things it will be taken care. So I hope I have answered the question. So you can also refer to my papers. So
Yes, sir. Definitely, we will refer it, sir. From audience side, if any other question is there, please kindly post in the chat box. Otherwise, we can wind up the meeting, sir. Sir, I think there is no question, sir. Thank you for your valuable presence and shared your research knowledge. After asking few doubts also, you have verified your PPT and we have correlated our questions, which was very effective for the participants, sir. Thank you once again on behalf of Realtek Multitech. Thank you.
thank you for the opportunity, and I thank the coordinators for this. Hope we will meet up in future. Thank you.
Okay, sir. Thank you so much, sir.
Thank you.